Good afternoon, everyone. I'm gonna explain about chapter 5, circular motion, the planets, and gravity. Okay, so let me share the slide. This one. Okay, this one. This is, I think, obvious. You can see maybe. This one. Chapter 5 is circular motion and planets. Okay, let's see. This is. And here's the outline is centripetal acceleration, centripetal forces, planetary motion, Newton's law of universal gravitation, the moon, and other satellites. Yeah, because a planetary motion is similar to something circular motion. That's why we study here planetary motion. And introduction, so you can in the maybe in radio news you can see the cafe to negotiate this just a curved way that but cannot go make this way just escape this one, then make big accidents, but maybe very slippery because might too fast speed run, or maybe this is ice road can slippery. Either the road surface was slippery or the driver was driving too fast for the sharpness of the curve. Then you're gonna learn why is that. All being toward in horizontal circle, experience acceleration because the direction of velocity changes continually. Hold on, let me see. This is a new twirling there, and then it's according to Newton's first law. If the string breaks, the ball flies up in a straight line. If you see Newton's first law of motion. If we motion is just if net force is equal to 0, net force is 0. Net force means the sum of all forces acting on the object. If originally was moving and just the rest case, it will be rest. Final velocity also rest, just keep rest. But if it was moving some certain velocity and moving, in this case moving, keep moving with a constant velocity in a straight line, And then you can see here is if I have some stone here, maybe that the rock there, that you twirl this twirl that can rotate it there. That a certain point it's broken. The thread is broken, string is broken, like that. In this case, this originally was moving this direction, that this keep moving like a straight line with the same speed, because there is no tension force. Originally tension force is hold this stone, but if this tension is string tension is broken, that no string tension, that this will move because no force acting on the. Of course, there is a gravitational force. Gravitational force is not this band. That is keep moving this direction. This is about the circular motion. And then here's the ball flies off in a straight line path in the direction in which it was traveling at the instant of string broken. Here we're gonna define centripetal force, centripetal acceleration. Centripetal acceleration is the rate of change in velocity of an object is associated with the change in direction of the velocity. Centripetal acceleration always perpendicular perpendicular to the velocity vector itself toward the center of the curve. Velocity is like here, going this one. Centripetal acceleration perpendicular to the velocity. Like this is the original. If that was rotating like that, in this case, velocity must be this direction. But centripetal acceleration is this direction. A centripetal acceleration this direction. Always the center of the this may be center of this is center of the circle. The center of the circle that this are point in the center of the circle. This is centripetal. That's why called centripetal acceleration. Then centripetal acceleration is related rate of change in direction of object that is associated with the change in direction of velocity. Even you think some object is rotating, just moving along the distance. This case may v equal to 10 meter per second. That keep same speed, 10 meter per second. But velocity is a vector quantity. Velocity is a vector quantity. And it has a magnitude and direction. Magnitude and direction. It's even it's the magnitude. The magnitude means the size 10 meter per second is not changing, but direction changing. Originally was moving this direction. The next time is moving this direction. Here is moving this direction. Here is moving this direction. Yeah, keep changing each direction. Then direction changing direction means this gives centripetal acceleration. Centripetal acceleration. Usually, acceleration is we defined. If I remind that is a change in velocity, rate of change in velocity. Usually, if we think just straight line case, we just think about just only magnitude changing, how fast to change magnitude. But in this case, centripetal acceleration will be special. That is only change in direction, not magnitude. Only direction is contribute to this one. Then here is the size of centripetal acceleration. What is the size of centripetal acceleration? You can see the velocity vectors, v1 vector, v2, two positions ball moving horizontal circle. And then here's initial like that. The final is here. Final v1 vector is going over the direction. That finally it's the vector is v2 vector is like that. Speed vector. Speed keep change. It's even its magnitude the same. If you move this is parallel, you can get here, right? That if you move v2 parallel, you can get here. Then this is once you know this one that you can find the vector subtraction. V2 vector minus v1 vector is v2 vector minus v1 vector is like delta v vector can be here. This one, this direction here. This is last time we learned. I think you can see appendix. If you have a vector, two vectors, it's how to get the subtraction is like here. If you have a vector, b vector like this, then a vector minus b vector should be from there's starting point from b vector to starting point a vector is connected. This vector is the subtraction of a vector minus b vector. We can similarly the starting point from v1 vector to v2 vector. This will be the subtraction of delta v vector is v2 minus v1 vector. Delta means, as I mentioned, the delta means some change in a quantity. This final quantity minus initial quantity. Delta is just a change in a quantity. That change in velocity will be delta V vector, can define like that. This is not algebraic, but just only this is vector sign. That means that it's vector quantity. It has a magnitude and direction both. Yeah. That the size of centripetal acceleration proportional to the square of speed and inversely proportional to the radius. I think this is something like related. That this is important formula. Centripetal acceleration related to the velocity and the velocity speed, that its magnitude, and divide by the radius. Radius is this distance, the distance from the center of the circle to the this point of the object here. This is radius. Radius are the same here. I think what you wanna see a video. I think. And I'm gonna show video. Okay, let me show the video. This video is maybe helpful to understand about centripetal force, centripetal acceleration.
One of the most confusing ideas about centripetal acceleration is that although the speed is not changing, we have an acceleration. This goes back to chapter 2, where we defined acceleration as the rate of change of velocity, not of speed. Recall that both acceleration and velocity are vectors. That means they have both a magnitude and a direction. So you have an acceleration whenever the velocity is changing. That would be a change in magnitude, the speed changes. A change in just direction, but the speed stays the same. Or both the direction and the speed could change. In centripetal acceleration, the speed is constant. So we have an acceleration simply because the direction is changing. Let's look at the equation in your book that relates to centripetal acceleration. This says that the magnitude of the acceleration is proportional to the square of the speed and inversely proportional to the radius. What does this mean? Let's look at velocity first. Since velocity is on the top, it means that if the velocity increases, then your acceleration increases. Since it's related to the square of the velocity, if we increase the velocity by a factor of 3, that means the acceleration would increase by a factor of 3 squared, or 9. Now let's look at the effect of radius. Let's assume that the speed is the same, but the radius decreases. So initially we have a circle with a radius like this and a certain speed, and now we have a circle with a very much smaller radius and the same speed. Recall that acceleration measures how fast we change, how fast we are going. If you're moving around a tighter circle, then your direction is changing more rapidly, so the acceleration is greater. You can also see this from the symbolic equation. Since as r decreases, a is going to increase. You can try this with a friend. Each of you will hold ends of a stout piece of rope, something that won't break. At first, keep it very short. and have the person on the outside try to move in a straight line. The person in the center pulls on the rope to keep the person moving in a circle. The person in the center will have to rotate also, or the rope will wrap around them. Now, lengthen the rope and try again. The person in the center should be able to feel that the force in this case is smaller than the force that they needed to pull when the circle was much shorter. This is a direct application of your equation for centripetal acceleration. As r increases, acceleration decreases, which means that your force, which is mass times acceleration, also decreases. Now, reverse roles and have the person in the center now on the outside, so both of you can feel the difference in the force. You can also use this experiment to feel the effect of speed. If the person on the outside moves faster, the person in the center will need to apply a larger force, indicative of a larger acceleration, to keep the outside person moving in a circle. Try it. Hopefully, you now have a better understanding of the relationship between radius and centripetal acceleration.
All right. Yeah, it's useful. You can watch this video in macro here. This is maybe a free ebook. And now I'm gonna come back to our slide. This is AC, R V scale that depends on velocity, and then a radius. This is it's a magnitude of course the same to magnitude means size. It's also same to like that maybe, but the direction changing. Yeah, but you have to remember that it depends on the speed squared divided by radius. And now we want to see what force produces centripetal acceleration. And we need to find what force can produce centripetal acceleration. Without centripetal acceleration, it cannot rotate. But here is, if rope is broken, in this case, centripetal acceleration is, if this broken, then this cannot make a rotation, just only keep going to straight line, right? But we need to find out what makes centripetal acceleration. When you twirling this rock with the thread, in this case, there is a tension force here, tension force here. Also, there is gravity, W is weight force here. And then if you have to decompose the tension force into horizontal component, like that, and a vertical component, they have to decompose horizontal and vertical component like that. That's kind of a rectangle, triangle. And then here is vertical component will be maybe vertically there is no motion. That is just only vertical height doesn't change at all. That means TV minus W equal to 0, right? Then F net force equal to MA, but A equal to 0. Acceleration, no acceleration. Vertical, that will be that F net will be TV vertical force. That is, we think this is a positive direction, upward direction positive, and then W is against the positive direction. That will be negative sign, is minus TV minus W equal to 0. Then TV vertical component must be same to the gravitational force. Then horizontal direction, we write to maybe horizontal direction. Horizontal, maybe this x direction, we can write equation of motion is maybe left hand side F net horizontal will be only TH horizontal component, that will be MA horizontal acceleration. Horizontal acceleration, that will be centripetal acceleration. That means AH will be centripetal acceleration. We learned V square over R, right? That TH equal to MV square over R. In this case, this horizontal component gives centripetal acceleration. The horizontal component of tension TH is the force that produces the centripetal acceleration. The vertical component of tension TV is equal to the weight of the ball, what I calculated here. And here's if we think of low speed case is V is small, then centripetal acceleration H is small. Then you have to see here's tension force is small. The horizontal component really decrease. Horizontal component also decrease like that. Angle is like that. TH values. If V is increased case, AH really big, right? Because AH horizontal acceleration, that is centripetal acceleration, V square R, that is really big, yeah. Then tension also, TH also increases really big. That's why it's tension. Even same tension force, but it's horizontal component is really huge. Even we know the vertical component exactly same to the weight, this one, but its horizontal component is really big. At high speed, the string comes closer to lying in the horizontal plane because a large horizontal component of the tension is needed to provide the required centripetal force. I'm going to see example 5.1. A ball has a mass of m equal to 0.05 kilogram. And then it's revolving at the end of the string. A circle is maybe example textbook 5.1. It doesn't 5.5 figures 5.5 or here is 5.5. Right, yeah, this figure is 5.5. Yeah, this figure. And 5.5, this figure. This is rotating. Its radius is with the radius of r is the 40 centimeter. 40 centimeter is in SI unit is 4.0 meter. And what's the centripetal acceleration? That V is also 2.5 meter per second. We need to find the centripetal acceleration. What is the centripetal acceleration? We may use the formula given there. AC equal to V square over R. AC equal to V square over R. V is 2.5 square divided by 0.4. This will be, once you calculate it, 6.25 divided by 0.4 is 15.6 meter per second square, because unit of acceleration is meter per second square. This is the answer of question A. Question B. What is the horizontal component of the tension needed? That's, T is here, that TH is TH. This works for this creates the centripetal force, centripetal acceleration. Then this is my vertical component will be same to the gravity, right there. Then we can see TH. We need to find the TH. Then TH equal to horizontal force only. There is a TH force there. The TH equal to the horizontal component of tension T is equal to M V square over R, right? F equal to F net equal to MA. But for rotational motion is A equal to V square over R. That's centripetal acceleration. Then this will be for rotational motion. Rotational motion is a rotational motion is, we can write to F net equal to just M V square over R, right? This is a formula for rotational motion. Using this one, we can see, like this one, this will be M is mass 0.05 times velocity is maybe velocity. Acceleration already calculated. This one is 15.6, because this is exactly same to AC. We calculated this one, already calculated that. This one, that will be 0.78 Newton. 0.78 Newton. This is a horizontal component of the tension force. And here we're gonna see centripetal forces. We call especially this kind of forces because its role is just to create centripetal action. Then we can call this kind of forces called centripetal force. Centripetal force sometimes can be tension, sometimes can be friction, sometimes can be some other gravitation force like attracting, like yeah. In this case, centripetal force is if that is very slippery case, cannot make a rotation. But in this case, centripetal force can be created by the friction. Friction force is avoid that prevent just escaped from the way. That's centripetal force is the net force that produces centripetal acceleration is often referred to as the centripetal force. That is not like normal forces, friction force. This is just a kind of force. Is just a rolling force. Yeah, right. The F net centripetal force is just simply mass times centripetal acceleration. Centripetal acceleration is V squared over R. Right? This is centripetal force. Then, sometimes the centripetal force can be friction in this car motion. Car is rotating. If there is no centripetal, there is no friction. The car is it's ice way, cannot make this rotation. Just go straight forward. Then if there is not motion in the direction of the force, we call it the static force of friction. This is static friction force because in this case, the car is not slippery. That case, we think relative motion is this is not slide. This case we can call static friction. If the object is sliding, maybe slippery, it might on the wet or icy surface, the kinetic friction is involved. This case, kinetic friction, yeah. And usually, kinetic friction is less than maximum static friction. You have to remember that. Friction. I think this there are two kind of friction there. If just this is a little bit confused about this. If I have this object, I that moving with the force maybe if we got 100 Newton, then this object started moving maybe with acceleration, and maybe with the velocity. And then in this case, we can see, there is a friction there. Friction, this kind of friction called kinetic friction. Kinetic friction. Friction means that is oppose the motion, right? Or is raised this motion that is opposite direction. Okay, this is a kinetic friction at when object is moving. That when object is at rest, maybe sometimes I apply to some force here. F equal to 10 Newton I applied that, but this object not moving at all. V equal to 0. V is not 0 case. This V equal to 0 just means at rest. In this case, even Newton's second law, if I think F equal to ma, that once we F net force equal F applied that this should be move, but it's not moving. This should be 0, but it's why? Because there is some friction force. Called this is static friction. That we think of F minus F static friction, that will be 0. Yeah. This is velocity is 0. That is right hand side should be 0. Then means in this case F static friction is same to the applied force 10 Newton. But here static friction has usually static friction is if we keep increasing this force, then also static friction is increasing. Then certain moment of time, this object is started moving. Yeah, if we increase almost maybe 99 Newton, maybe 101 Newton, that is started moving. In that case, this static friction is converted to kinetic friction, right? That case, this maybe if static friction maximum force can be 101 Newton. That this 101 Newton is after started moving, the object can move easily. First time actually when you push the object, and then first the moving is really hard, but it started moving, that easy to move. Yeah, because static friction is larger than kinetic friction. Initially, it's moving is really difficult, but it's, later kinetic friction less than that. That's why F static friction, maximum static friction is higher than F kinetic friction. This is kinetic friction. Kinetic friction. This is called static friction. Static friction. This is called static friction. This is kinetic friction. This is the centripetal acceleration of car rounding or level curve is produced by frictional force exerted on the tires by the road surface. This frictional force can make prevent this car just escape from road, yeah, fail to the curve, yeah. And when the curve is backward case, horizontal component of the normal force and H can exerted by the rod of the car can help to produce centripetal acceleration. Normal force. This normal force means at perpendicular to the surface. Yeah, supporting surface, support surface, support surface. And support surface here, that this is support surface here, then this normal force must be perpendicular like this one. This normal force is like that. But normal force can be decomposed into horizontal component and a vertical component. That is horizontal. Here is maybe center of curvature. Center is rotating this way, like this, rotating like this way. But in this case, this component work for centripetal force. Yeah, this horizontal component provide centripetal force. Then this vertical component also can be balanced with gravitational force. Gravitational force. Gravity is downward direction. Then this and vertical component will be the same, but this is horizontal component of NH. This NH will work for create centripetal acceleration. Yeah. Then here is the horizontal component of normal force NH is exerted by the rod of the car, help to produce the centripetal acceleration. Also, we can see writing PHYS here according to Newton's second law. We can write maybe writing PHYS here. Writing PHYS here. PHYS here. There's no E there. That here is, this PHYS seems to be this rotating. Then here is when she is here, that there is something that this is base support, the rod support to maybe sit there, and then here is she is rotating here. In this case, radius R. Then we need to find the forces acting on her. There is gravity there. Gravity of message. Gravity is mg. Maybe that is sometimes called just a double weight force. And there is a normal force here, n force here. Then here, acceleration must be, in this case, acceleration is this direction, AC. Yeah, because centripetal acceleration always point to the center of the rotational center, yeah, center of the curvature, right? Then we can write the equation of motion is F net equal to MA. In this case, F net equal to, we choose this direction is positive direction. and then N will be positive, N will be positive, minus mg is negative because gravity is downward direction. And then m times acceleration, in this case acceleration AC equal to v square of r, right? R, maybe r. This log is the r. Then acceleration we can write to mv square of r. We can write that. This is Newton's second law. This is Newton's second law of motion. That is net force is this is net force, this is net force, and this is net force. This is just centripetal acceleration, right? That we can write that. In this case, we can find the normal force. N is normal force. Normal force means normal force is just the chair, the seat pressing on her, yeah, pressing her, yeah, acting on her, yeah. Okay. This is it will be N will be mg plus mv square over r. Then that's why she can feel this baby. The bottom side is really hard to press the normal force. Then this is right there. This is very serious bottom. Then if she is, this is when she was at bottom of the path, the bottom place, maybe bottom place. But what about when she is top place? When she is top place, she is top place. She is here. She is here, and then here's she is like maybe flipped like that, and then her head here, and then it's her the gravity is here, like here, gravity mg here, and also here is seat here like that. The normal force also acting on this direction. In this case, you know, acceleration is this direction, centripetal acceleration, always pointing center of the curvature like that. Then we can write the equation of motion. In this case, we can choose positive direction is this direction because acceleration direction is like that. Then we can choose positive direction. F net equal to ma. This is Newton's second law. Then we know F net is equal to normal force plus mg, both the same direction, right? It's positive direction. That's why we have to add the positive sign there. This is positive both. Then acceleration also positive. AC equal to v square over r. V square over r. Have the r maybe. Here's the radius is r. M v square over r. Yeah. V is a speed. This is how fast she is rotating. This is how fast she is rotating. Here's V is also how fast she is rotating. V is how fast she is rotating. Then in this case, you can normal force will be m v square over r minus mg. As m v square over r over minus g. As I think at top there, this speed is really slow. Yeah. No, the speed, the force is less than that. This is top place. This is bottom place. Yeah. This is maybe larger than and bottom. In this case, and bottom is and bottom must be larger than and top because you know this is subtraction. This is addition. Yeah, even if we think this two speed is same at here and here same, normal force different. Then you can see it's in writing PHYS here, according to the Newton's second law, the normal force exerted by the seat combined to produce the centripetal acceleration for rider on the wheel, PHYS wheel, and then the top of the cycle, the net force must equal to the mass of the rider, times the centripetal acceleration, which is now directed downward, the W minus M. That here's we can normal force can be different. Here's N will be we can write N will be W plus MAC. In this case, N equal to W minus MAC. Yeah, that is this is N bottom. Bottom case, top case, bottom is top case that we can take, and bottom is larger than and top. That she feels strong supporting force here, but she feels here is less. This is small supporting force top. Here is a big supporting force and bottom. I'm gonna explain about the planetary motion. And early models of the heavens, people thought that Polaris lies near the center of the pattern and does not appear to move very much. The entire pattern appears to rotate during the night. This is Polaris here. All others is rotating around the Polaris. Early philosopher scientists has an Earth-centered view or geocentric view of the universe. It's famous is Galileo. He claims, the Earth is the orbit around the sun, but it's or maybe all the Roman Catholic they claimed no Earth just center, then the other planets or stars orbit around the Earth. That's wrong eventually. And the Greek philosophers developed the early models of the model motion of the heavenly bodies involved a series of concentric spheres centered on the Earth. Here it's Earth, then all others moving around the Earth. Then the planets sometimes appear to move backward. We think so. We cannot. They thought in this case we think maybe 5.3. 5.3 planetary motion. Planetary motion. Then they think this Earth is Earth here, and all others are orbiting around here. Orbiting around that, but there is some objects should be all going to the same direction, but some objects going to one direction that is going also sometimes backward like that. Why is like that? They thought they claimed some other model. It's Ptolemy's, I think, suggest model is the planets sometimes appear to move backward, like going forward, backward. This is going this direction, but this direction is opposite direction. Going there. They're also going this direction. There's this kind of motion is called retrograde motion. Retrograde motion against the background of the big stars is called retrograde. But then how to explain this one? Then some Ptolemyus is that Greek scientist. He a philosopher is 2nd century AD. He devised a model that used the circular orbit rather than sphere but still geocentric. He invented the idea of epicycles. Cycles rolled like planets moving here. That in this case maybe going this direction. In this case this is going rotating around here. Then going this direction. Yeah. That this planet moving like this one. That in this case going this direction. At this point it can be opposite direction. Yeah. He suggests this kind of model. It's very smart way, right? Retrograde motion can explained by his model. In the 16th century, a Polish astronomer, Nicolaus Copernicus, put forth the sun-centered of heliocentric view later, championed by Galileo. Yeah, actually, I think we thought Galileo first about Copernicus already. They suggest this one as the Earth passes the more slowly moving Mars appear to move backward as seen against background of much more distant pixel, right? And then Danish astronomer Tycho Brahe, he is developed a large quadrant that he used to make a very accurate sighting of position of planets and stars. I think he did this a lot of experiment, just a whole life he spent for observing. Whole life he spent to observe the stars, stars, that planets, and then he pretty accurate data collect. Then his student is maybe Kepler. Also, he developed Kepler's. He analyzed with the data. Then he used best mathematics. He just analyzed his data. He got maybe Kepler's first, second, third law. Here's Kepler is Tycho Brahe's that analyzing data collected by Tycho back to his assistant Johannes Kepler. He is also a Danish physicist, astronomer. After Tycho's death, that he suggests three laws. The planets all move in elliptical orbit, not exactly circular orbit, just elliptical orbits about the sun, with the sun located at one focus of the ellipse. Maybe here's the sun, here will be here's maybe sun, here might be that. This is also like a planet, is maybe like the Earth or some Mars or Venus orbiting around there. Yes, there may be sun here, the orbit around there. Then the second law is like an imaginary line drawn from the sun to planet moves through equal areas in equal intervals of the time. If we count 25 days, this striped area with the radius, this is sun, this is planet, sun. Maybe we think this is a planet. Just planets like, such as the Earth, Venus, maybe Mars, Jupiter, like that. This maybe 25 days moved there. That we can calculate this area, how much it striped this area, and then also another way is 25 days. This area is the same. This area is and this area is the same. Area is the same. Then to this looks triangle, to the same that, but this is height is really big. Instead, this basis is small. But in this case, this really long, but this height is small. That this is very big distance. But it means very fast moving. Right here should cover fast moving, but this is slow moving. Even same day to this distance is this short distance, this is long distance. Means this is slow, this will be fast. Yeah. This is the second law, Kepler's second law. And then the third law, T is amount of the time taken for the planet to complete one full orbit around the sun period. Then if R is, this is called T is period. Yeah. Period means period means just how long does it take for complete one cycle. Here sun, that the Earth is complete one cycle. How long does it take one cycle? That would be 1 year. Like 1 year is 364 5.2, maybe, as I remember, 24 days. This is 1 year. That is a period of the Earth. This is Earth, but the other period will be different for different planets like Venus, Jupiter. But those guys has some rules there. Here's if we have something like here. I guess I don't remember. I don't memorize it. Or sun here is maybe there is a lots of some. Yeah, here's maybe the Earth is Earth here. Earth here. or the radius, maybe it's a radius like here, maybe I think R Earth, and then also the other one is maybe Jupiter, maybe this is RJ, but here is you know there is a rule is T. Yes, T square over R third power is radius. The third power is all same, all the same. This maybe T square, or maybe this Earth's period square over R Earth period third power is same to the T Jupiter's second power. Jupiter radius third power is same. This maybe other all the non planets. Yeah, this all is the same. This one. Now on this one, maybe T Mars, and R Mars. Yeah, this is one criteria for determining this is exactly a planet or not. Yeah, if that is not planet, maybe you can think that is asteroid or some other can be star. Yeah, then we can determine. Sometimes I think Uranus is sometimes excluded from the planet or not. That when we decide judge whether this planet is a real planet or not planet, you can use this kind of formula. This this radius, and then also a period. Period means how long does it take to make one turn. All right. Yes, for the Earth, this will be 365 days. Then also the other planet is different. Yeah, maybe the Moon is not a planet. Why? Because Moon cannot satisfy this formula. It's not T Moon square divided by R Moon third power is not the same. Yeah, this Moon is not planet. Yeah, this is Kepler's third law. If T is the amount of time taken for the planet to complete one full orbit around the sun, period, and if R is the average radius of the distance of the orbit around the sun for each planet, then the ratio of the square of the period to the cube of the radius, T square of R third power, is the same for all of the known planets. Right? This is the three laws of Kepler's three laws of planetary motion. It's very important, and this will be later analytically derived by the Newton's mechanics. Yeah, Newton derived this one also. We're gonna solve one example problem. How long does it take Mars to complete one orbit around the sun? The distance of Mars from the sun is 1.5. R. Maybe here's this sun. This is Mars. This radius are radius is 1.5 AU. Then AU is the average distance from the Earth to the sun. That RE will be 1 AU, right? The radius the Earth's orbit is 1 AU, right? This maybe radius is they use the lowercase. I use the capital. Then how long does it take Mars to complete? How long take that T Mars period of T period for Mars? We need to find it. But T period of the Earth is just 1 year, right? 1 year, 365 days. You can see, and then we can use third law, Newton Kepler's third law, and T square over R third power. T square over R third power. Third power is constant. Then using this one, we know T Earth square divided by R Earth's third power equal to T Mars square divided by R Mars third power. Yeah, that's cubed. The same. That here is T period of Earth orbit around the sun is 1 year. 1 year squared. 1 year squared, and then radius is 1 AU. Third power. That here is right hand side T Mars is 1 point. No, we don't know. We need to find T, the Mars scale, and then Rm is 1.5 AU third power. Then we can find how to find the Tm scale. Tm scale will be 1 year squared divided by 1 AU third power times 1.5 AU third power. And here's astronomic unit is cancelled out. That this will be can be Tm will be square root 1.5 third power 1 year squared. That this is 1.5 the cubic power square root then 1 year. 1 year. That once we calculate this one, 1.5 the third power, no, 1.5 third power, you can use your calculator. No, calculator. It's my calculator. 1.5 third power, 1.5 third power is 3.375 times 1 year. That will be 3.37. Square root, take square root will be, it's 1.837, 1.837 year. That would be, if we think 1 year is 360. This is Earth year. This will be answer. Then how to think that is date times, we know 1 year is maybe 365.24 days. Actually, 300 some years 365 years, some years 366 days. That's average 365 to 4 days. So then we can multiply by 365.24. That would be the 1.837 times 365.25. That would be 670. That's 670.96 days. That is the time for there was this is the Mars complete one rotation. That is make one revolution can be 670.96 days. Right, the next one is gonna see Newton's law of universal gravitation. Okay, gonna see Newton's law of universal gravitation. And Newton is achieved already the 3 laws of motion. Is first is the law of inertia. The second is F equal to ma. The third equation is just action and reaction. That is another law that is called universal gravitation. It means 5.3. 5.4 Newton's law of universal gravitation. Not just he did experiment, like maybe the Earth is in Newton's era. People know so maybe the Earth is around just sphere shape, and then if there is a tower there, that they shoot the rock there. That if speed is small, they can drop here. If you increase the speed, is like here, right there. If you do here, that or can be maybe turn around like that. But this is rotating. Why? Because the Earth attract the projectile like that. That would be rotated there. This kind of idea is developed by Newton. Newton imagined a projectile fired from a incredibly high mountain. If fired with a large enough horizontal velocity, the projectile falls toward the earth, but never gets there. It gets there. That's like, oh, this is kind of, satellite around. But why is that this is rotating? Rotating motion is kind of, as we see, rotating motion, to make this rotation, we need to have some centripetal acceleration. The centripetal force must have some centripetal force. What can create to produce a centripetal force? In this case, the Earth is attracted. The Earth, this guy is attracted, that this can keep the rotating like that. The Earth is attracted to the projectile like that. And then Newton is maybe suggest universal gravitation, not only Earth, but also any object. Maybe you can think between you and your brother or your sister, as here's it, your brother, and you put your mass there, that attracted by them. If you attract it here, that this will attract each other. Right? That the force is maybe you and your sister attracted, not only maybe your sister, maybe or brother attracted, because you have mass. The mass amount of mass is related to F is G times your mass times your brother's mass. This your mass is M1. Your sister's mass is F2. That also depends on the distance between this distance that R squared. But you cannot feel the force. Why? Because this G is pretty small. How small that is? G equal to 6 times 6, 7 times 10 to minus 11 power Newton meter square per kilogram squared. Because your mass is pretty much just maybe 30 kilogram, maybe 100 kilogram, even 100 kilogram, but it's denominator maybe 1 meter squared, that be 6.6 times 10 to minus 11 power. That you can see this is 10 to fourth power, that will be about 6.6 times 10 to minus 7 power Newton. It's very tiny. You cannot feel this force between you and your sister. But if we think about planetary object, that situation can be different. Mass of the planet is the Earth, I think, very 10 to my 24 kilogram, really big. This maybe mass of the Earth is big. In this case, this is significant. This kind of maybe Earth and Sun is significant. The person. Yeah. Also, we can think maybe Earth and Moon. This force is significant. Yeah. Because the mass is big. Yeah, the force is F equal to G times G is gravitational constant. Gravitational constant never change. That is gravitational constant. Sometimes called universal gravitational constant. Universal means never change. Just universal gravitational constant. But here's mass, two mass, product of two mass. Then R is distance between them. Distance between them. Yeah. This R. Right. This is shown here. The gravitational force between two objects is equal to the mass of each object and inversely proportional to the square of the distance between the centers of masses. F equal to G M. G is that universal is constant. Universal gravitational constant. The direction of the force is attractive and lies along the line joining the centers of the two masses. Like here, F1, the F1 vector and F2 vector is magnetic same. It's because that is a kind of accident reaction force. Because M1 attract M2, the M2 also attract M1. This force is the same, but opposite in magnitude. This force may be 100 Newton. This also 100 Newton, but this will be maybe negative. This force is depend. If this guy is 200 Newton, this will be also 200 Newton. Same, yeah, same in magnitude, but opposite in direction. the gravitational force is attractive and acts along the line joining the center of two masses. It obeys Newton's third law of motion, that's action and reaction pair. And here is how is weight related to the law of gravitation. Okay, we can think about this one. The Newton's law of gravitation force on person must be GME, like that. This we can't the gravitational force of maybe our gravity weight is just weight is gravity force. Then if we think me and I is here, I here, then my mass m, that mass of the earth here, that maybe you have to think of the center of the earth, that this the radius may re, and the distance between me and the earth is like this from me to the center of the earth, that we can find the force F equal to G me, that is mass of the earth. I mean mass of earth, mass of the earth, that R is radius the earth, radius of the earth divided by R E squared. This is exactly same to mg. G is acceleration due to gravity, 9.8 meter per second squared. That we know, my mass is cancelled out, that we can find G is acceleration due to gravity, G times me divided by R E squared. This acceleration due to gravity. I think if we can check this one. This is 6.67 times 10 to minus 11. Then mass of the earth is mass of the earth. What is mass of the earth? Mass of the earth is, as we remember, you can find maybe appendix. You can see appendix in the textbook. Yes, appendix. And maybe decimal fraction. I think, yeah. We can find the mass of earth. It's you can find it in Google. Mass of the earth is 5.97 times 10 to 24 kilogram. Yes, you can see 5.97 times to 9. Yeah, this is the mass of the earth. And then we can see use the mass of the earth. 6 times 10, mass of the earth is m is 5.97 times 10 to 24.2 times kilogram, 5.97 times 10 to 24 divided by radius of Earth. Radius of Earth is 6,370 kilometer that we need to change in SI unit. That will be 6.37 times 10 to 6 power meter. 6.37 times 10 to 6 power. If once you calculate this, it will be approximately 9.8 meter per second squared. So you can check this statement by yourself, by using your calculator. That is, yeah, as a on the slide. What the slide? Where's the slide? I cannot find the slide here. Yeah. The Newton's law, m is the mass of the person, and m is the mass of the earth. It's not me. So this should be changed. me. Oh, computer is slow. me. And this is should be lowercase. subscript ME. M is the mass of the earth. This gravitational force is the weight of the person. We can also express the force as F equal to mg, mass times gravitational acceleration. But those two expressions for to be the same g, the gravitational acceleration, g is, this is 9.8 meter per second squared. 9.8 meter per second squared. Yeah, this you can use g equal to 6.67 times 10 to minus 11 Newton meter square per kilogram square. Also, ME is, as I mentioned, 5.97 times 10 to 24 kilogram. And then R is 6.37 times 10 to 6 power meter. So, put this stuff, so you can check this one. I want to watch the video. Okay. That's
Newton's law of gravitation states that the gravitational force between two objects is proportional to the mass of each object and inversely proportional to the square of the distance between them, where g is a constant. And the direction of the force is attractive, always, and lies along the line joining the center of the two masses. Let's translate. If either of the masses increases, the force will increase, since mass is directly proportional to the product of the masses. If the distance between them increases, the force will decrease, since force is inversely proportional to the square of the distance. How much does the force increase? Let's look at the masses first. If M1 is replaced by a mass 3 times bigger, then the force will be 3 times bigger. If one mass is increased 4 times and the other mass increased 5 times, then the force will be 20 times bigger, since 4 times 5 is 20. What if one mass is increased 4 times and the other mass is decreased by 1/4? Then the force will not change, since 4 times 1/4 is 1. Now let's look at distance. Since the force is inversely proportional to the square of the distance, this requires 2 steps. The first thing you want to decide is if the force is going to increase or decrease. If the masses are further away from one another, then the force decreases. They don't have as much effect on one another. If the masses are closer together, then the force will increase. Then look at how much. Since the force is related to the square of the distance, you have to take this into account. Let's say the distance increases 3 times. The force would decrease since the masses are further away. 3 squared is 9, so the force would decrease by a factor of 9. In other words, if the force had been, say, 216 newtons, it would now be 216 newtons divided by 9, or 24 newtons. What if you get closer? Then the force increases, but by how much? Let's say you start at a certain distance r apart. Then you move closer, so you are now only r over 3 apart. What happens to the force? It becomes 9 times larger, since 3 squared is 9. Of course, it may be that both the masses and the distances change at once. Let's try one. Let's compare the force of the original situation to one in which M1 increases by 3, M2 increases by 4, and the distance increases by 6. Because of just the masses, the force would be 12 times greater. Because of just the distances, the force would decrease. Your distance has increased by 36 times. Putting these together, the force will change by 12 over 36, or 1/3. So it will decrease overall by a factor of 3. Let's try one more. Compare the force of the original situation to one in which M1 increases by 2, M2 increases by 4, and R decreases by a factor of 3. Because of just the masses, the force will be 8 times greater. Because of just the distance, the force will increase by a factor of 9. Putting these together, the force increases 8 times due to masses increasing, and 9 times due to distance decreasing. So the new force is 72 times greater than the old force. You can imagine many more scenarios, I'm sure. Try it.
Right, and we're gonna move to the slide here, and the mass of the Earth is 5.98 times 20. This mass of the Earth, ME equal to 5.5 times 98 times 10 to 24 kilogram. Then average radius is RE radius is 6,370 kilometers. That would be 6.37 times 10 to 6 power meter. Find the gravitational force acting on 50 kilogram person standing on the Earth's surface. That we have to find here is, Earth is here, the person here, that the distance between them, this is RE. Maybe size of person is ignorable size of the Earth, because size of Earth is really a big meter, but human size just only 1 meter, maybe the tall guy 2 meter. This is compared to much smaller than, we can ignore that, only we can think this one. That gravitational acceleration, first we can use gravitational acceleration. We can use just the force is W equal to mg. Simply can calculate this one. That's 50 times 9.8. This will be 490 Newton. Question B, by using Newton's law of gravitation, that we can find that F equal to G ME times your mass, 50 kilogram mass divided by RE squared. This is 6.67 times 10 to minus 11 times mass of the Earth is 5.98 times 10 to 24 times mass of the person is 50 kilogram divided by radius of the Earth is 6.37 times 10 to 6 power squared. That once you calculate this one, is about 409 Newton. 409 Newton. That is the same. All the calculations, this one, same. We can calculate this. Maybe we have. Let me check with my calculator. 6.67 times 5.98 times 50 divided by 6.37 squared. That's 49 49. You can see like 449.149 times 10 to negative 11 plus 24 minus 12. This is 10 to 6 power. 12. That will be 491.49 Newton. Yeah, this is this and this is approximately correct. Yeah, maybe how much difference? It's just only 1 Newton, 1.5 Newton difference is just divided by 490 compared to this 490 is just less than 1% error. It's really pretty close. You did experiment. I think maybe later you can do experiment. what is your experimental error? Pretty small, maybe next time this Thursday you're gonna do a lab, so PK-based lab, like you're gonna measure gravitational acceleration 9.8. That maybe if your measurement really correct, but I think if you get maybe 9.7, 9.6, yeah, the measurement error can, but this is pretty close to each other. That's why that we can prove all gravitational Newton's law of gravitation is correct. Yeah, actually. And here's section 5, the moon and other satellites. Moon is also orbiting around the Earth. Sun is here, and then the phase of the moon depend on the positions of the sun, the moon, and the Earth. Moonlight is moon cannot illuminate itself; it just reflects sunlight, right? Sunlight here, moon is dark part. Here is the sunlight here. Then you can see a reflected one here. By my eye here, you can see. And when the moon is full, it is on the opposite side of the earth from the sun. Yes, this is a full moon. Opposite side of the this is full moon. That's the sunlight here, just that you can see, just the reflected one. And when they aligned, and we see the side that is fully illuminated by the sun. When they aligned in order to sun, earth, moon, or sun, earth, moon in a line, there is a lunar eclipse, right? Sun is the sun here, sun, and then earth should be, maybe we can see green. This is earth, the sun, then here's moon. Moon is maybe blue moon. Moon is a blue. You can see this blue moon here. Moon. And that's lunar eclipse. Yeah, just because the Earth is just block the sun exactly. Then moon cannot illuminate because it cannot get reflection. That this is exactly dark. This is a lunar eclipse. But also, when the moon is in the right position of to cast the shadow on the Earth, solar eclipse. Solar eclipse. If sun like is daytime, the sun is here, but here, so moon is here, our earth is here, and then this moon is block the earth, sunlight, that you can see something shadow there, shadow, some shadow is like shadow. This is the solar eclipse. This is lunar eclipse here. And I'm gonna see here is the lunar eclipse geometry. This is a solar eclipse. You can see this one. Sun is like here's the Earth. There is something like this kind of shadow there. This is a solar eclipse. Even daytime, but it's a really big shadow. It's a very, maybe human here is suddenly become dark during the daytime, like the night. This is a lunar eclipse. And does the moon obey Kepler's laws? Like the planets, the moon's orbit is on ellipse, but with the Earth at one focus of the ellipse rather than this sun, right? You can draw like here, this ellipse here. There are two focuses here. One focus here, another focus. That there is Earth here. This Earth here. Earth is green Earth, and a lot of trees there. The moon is orbiting around the Earth along this ellipse. This orbit actually not looks like this. Just almost like a circular orbit, like very close to the circular orbit. Also, it follows to the law of Kepler's third law, like this kind of law. And then this period of the if that is maybe this is Kepler's third law of planets. This is like this planet, this for satellite. Saturday. If we can determine that the object is maybe cosmic object is Saturday or not, we can use this formula. Yeah. But if that is a planet or not, we can use this formula. This ms is mass of the sun. This is me is mass of the earth, right? This is for Saturday. Yeah. There's a moon is kind of a satellite of the earth, but it's different from artificial satellite. Artificial satellite is also can satisfy this formula. Artificial satellite orbits of artificial. Any satellite orbiting the Earth must have the same value for the ratio of T square over R third power. Always this will be constant because mass of the Earth doesn't change at all. Then G is a universal constant. Yeah, but this is 4 pi square over G ME. That is mass of the Earth. This is always same as I see 5.98 times 10 to 24 kilogram. Then G is 6 times 6, 7 times 10 to minus 11. Always the same. That this must be constant, right? That's all. Yes, I hope you can understand this one, and maybe I will record the next steps maybe on Thursday. That's maybe chapter 6, energy oscillations. Okay, have a good day.